Hi, everyone. Thanks, Randall, Laura, for giving me the opportunity to talk about one of my favorite topics, which is measuring supermassive black hole spin with far UV and X-ray observations. Can you see my slides? Just someone if...
Yep,
Okay.
It looks fine.
Great. According to the Noether theorem, black holes can be completely defined by three parameters: their mass, spin, and electric charge. In reality, a charged black hole will be neutralized by discharge to its surrounding. So black holes basically can be defined by their mass and spin. The masses of the stellar mass black holes within our own galaxy are typically determined by examining the orbital and radiative properties of their companion stars. The masses of supermassive black holes can be estimated from various techniques, including reverberation mapping that we heard about it yesterday, some of the host galaxy properties, such as the stellar velocity dispersion and emission line originating in the broadline region, among other techniques. However, most of these methods rely on measuring radiation that are emitted far from the black hole itself. So each of these methods have their own uncertainty and caveats. However, a robust estimate of black hole spin can be even more challenging than the mass. But before getting into the details of the spin estimates, let's see, why do we care about the spin of the black hole? The spin provides key information on the accretion. Oh, I'm sorry, somehow. Oh, am I still there?
Yep, we still see your slides.
Oh, okay. I received a notification on my laptop and it just exited me. So sorry. Spin provide key information on the accretion and merger history of supermassive black hole by creating, basically they are creating a fossil record. For example, a low spin value may reflect that the supermassive black hole grew by chaotic accretion processes, such as major mergers. But a low spin value may indicate more of a dry black hole mergers or a steady accretion. In the standard picture, the central supermassive black hole lies within a geometrically thin but optically thick accretion disk, where gas flows and settles into circular orbits, and the gas loses angular momentum as it moves inward. At each instant, gas occupies a circular orbit appropriate to its instantaneous angular momentum until it reaches the innermost stable circular orbit, or ISCO, which is shown on the left side. Inside the ISCO, gas falls dynamically onto the supermassive black hole. Therefore, this ISCO is the inner edge of the accretion disk. The right panel shows that ISCO varies monotonically with the black hole spin. So as this innermost circular orbit decreases and gets closer to the black hole, basically as we move from negative to positive spins. Here you can see this in more details. The plot on the left shows a case of maximally spinning prograde black hole, which means that the black hole and the accreting material are rotating in the same direction. As black hole spin decreases towards zero, ISCO moves further out from the black hole and increases the size of the gap between the edge of accretion disk and the event horizon. This gap is going to be the most for the case of maximally rotating retrograde black holes, which means that the black hole and the accreting material are rotating in two different directions. Supermassive black holes can be spin can be estimated through various techniques that I listed them here. Each of these techniques are based on some initial assumption and therefore inherit some uncertainty due to those assumptions. But the first supermassive black hole spin measurements became possible by coupling theoretical models to high-quality X-ray spectra. The method estimates spin from relativistically broadened ion K-alpha line arising from the harder X-ray emission reflecting off cold matter on the accretion disk. So for this method, we need high signal-to-noise spectra, and therefore this method can be limited to nearby AGN, and up to now we have the spin measurements with this technique for a few tens of AGN at very low redshift. Another issue with this technique is that the scattering and emission components may mimic the signature of the reflection, so our spin estimates could be affected by that. So other techniques for measuring the spin were developed, such as continuum fitting and the other methods that I listed here. The continuum fitting is based on modeling the observed visible to X-ray continuum emission from the accretion disk and corona. This method can be applied to any types of AGN, radio loud, radio quiet at any redshift, so it is more general than the X-ray techniques. In the continuum fitting method, we fit the optical to X-ray SED simultaneously using some accretion disk modeling. Some of these popular models are included in XPEC, such as CARE-BB, Optics AGNF, QSO-SED, among others. And similar to the X-ray reflection method, this method is also developed based on the geometrically thin, optically thick disk with Eddington ratio between 0.01 to 0.3. However, one of the challenges of this method is that it requires a broad and simultaneous wavelength coverage, which usually exceeds the capabilities of a single observatory. However, this will be less of an issue for Arcus with simultaneous far UV and X-ray observations. Additionally, for a robust estimation of black hole spin, independent black hole mass and disk inclination and redshift are required, which we can get those from the optical data. To show how important the spin is in the shape and normalization of the accretion disk SED, here I show the accretion disk SED generated by QSO-SED model of Kabuta and Don 2018. I created these templates by varying black hole mass, Eddington ratio, and spin, and these parameters are for a quasar at redshift around 1.5 at 30 degrees. So the plot here is in log luminosity versus log frequency, and in each panel, the black hole mass increases from 10 to the 7 to 10 to the 10 solar mass from green to pink. The Eddington ratio increases from left to right, but is fixed in each panel, and the spin increases from 0 on the top panel to bottom, which is spin 1. What these plots overall show is that an increase in black hole mass moves the peak of accretion disk SED to lower frequencies, resulting in a cooler but more luminous accretion disk. But an increase in Eddington ratio or a spin moves the peak to higher energy, resulting in a hotter and more luminous disk. The black region here roughly shows the frequency region that Arcus can recover. So Arcus can simultaneously trace the peak of accretion disk emission along with the soft X-ray tail of it, which makes it great for spin measurements in continuum fitting method. Here, I'm going to show two examples. One is from Collinson et al. 2017, showing how a combination of optical UV and X-ray data can robustly constrain the peak of accretion disk. That one is on the left side. And on the right side, you can see a multi-wavelength.
2 minutes.
I'm almost done.
Great.
On the right, you can see the multi-wavelength SED from radio to X-ray. So the shaded region here again shows Arcus frequency region. So you can see that the far UV data can constrain the peak of accretion disk emission and with the soft X-ray at the tail. So we can constrain the accretion disk much better and have a better estimate of the spin. But what is interesting in this particular case is that this is a radio loud example. So basically we can use Arcus and such sample and provide an independent constraint of a spin, which we can then use to look into the relation between the jet power and supermassive black hole. With these two examples, I'm going to end my talk, so please let me know if you have any questions. Thank you.
Okay, thank you very much. Very interesting. So we have good time for questions. I've not seen anything in the chat just yet. Do we have any questions?
Mojegan, excellent talk. Oh, sorry, let Laura go first.
Hi, Mojegan. Yes, to echo Randall's sentiment, thank you for the talk. Question for you, looking at this SED that you have on the right in particular, I'm assuming that the two black bands indicate the Arcus FUV and X-ray bands. So if you have data in those two bands alone, and you're interpolating everything that happens between, how uniquely can you determine the solution for a given black hole spin? I mean, are there other parameters, for example, that would be degenerate and give you a similar solution, accretion rate, for example?
Yes, but that is generally the case for all the SED models, so you need more data to basically constrain each of these parameters better. So if you only have those two wave bands, it's not going to be enough because you need an estimator, you need an independent estimate of black hole mass at least. So you need some sort of optical data to have that.
Okay, thank you.
Randall, did you have a question?
Actually, it was about the same question that Laura asked. So,
but I want to emphasize that this is kind of inherited in all SED models. In broadband SED modeling, this is the case, not just this particular sample or this particular data for Arcus. It is inherited in SED modeling.
okay, thank you.
I have a question for you. How would dust confuse the analysis? And do you have a method to correct for reddening in the vicinity?
Oh, yeah. So the one that is from my own paper on the right side. So the way that this SED model is done, it's this is a quasar. So we have more obscuration from the torus, less of contribution from the host galaxy generally as optical bands. So I start by fitting the torus component, then I correct the optical UV part of the SED for the obscuration from the torus, and then I feed the accretion disk model to the corrected SED. But when you do that for type 2 sources, it will be different because you need to fit the host galaxy first and then correct for the obscuration from the host galaxy at optical UV band and then do the rest of the fitting.